So yeah, like Travis said, this thing sucks. I'm going to try and talk to you about how I characterize the diversity of atmospheres from exoplanets to brown dwarfs. It's a very vague title, but that's okay. So you guys have probably seen this plot 475,000 times now. So if you plot up kind of a set of the exoplanets for which you have masses and radii, if you plot mass here, and if you plot temperature down here, this is kind of the lay of the land, so to speak. So oftentimes you have these guys here that are on the order of the size of Jupiter, really hot. These are called hot Jupiters, 2000 Kelvin. Objects in this regime are sometimes referred to as warm Neptunes. And then you have these super Earths. These names are all really dumb, and I'm sure they'll change in due time as we find more of these objects. And then you have these guys up here occupying this space. These are the brown dwarfs, so they're higher mass than most planets. That's why they're not planets. And then, of course, this is our sort of slice of solar system, kind of the masses and temperatures that our solar system spans. So the kind of take-home message from here is looking at all of the exoplanets, we see that there's a lot more diversity in even just these two slices of the infinitely sized parameter space here relative to our solar system. So there's a lot to be learned by both brown dwarfs and transiting extrasolar planets about the atmospheres of these objects compared to what we can get from our solar system. So we have really good data for our solar system, but we have a limited amount of diversity. And then right now we don't have so much good data for a lot of these transiting planets, but we have a lot of them. So there's kind of like a trade-off. It's like a numbers versus signal to noise game here. So what I'm going to try and talk about is what we can learn about these different classes of objects here. So the idea is that we can understand atmospheres now within a statistical context, with beyond just having the 9 or however many planets are in our solar system now. I lose track half the time. We can use the large numbers to help address issues about the processes happening in planetary atmospheres. So this is kind of my little cartoon putting people in boxes idea, where astronomers sort of think of a planet as just a black dot that passes in front of a star during, say, a transit. And from something like that, you can measure the mass and the radius of the planet. That gives you the density. If you have the density of a planet, maybe you can put together a simple structure model to figure out, maybe it's got a core, maybe it's got some, liquid ocean, and it's got some atmosphere on top. And so I think this is where planetary science really starts to come in, and where the things that I am interested in studying start to come in. So a planet is more than just a black dot passing in front of its star. Well, let's skip that. It's got all sorts of exciting things going on. So things we might want to know about an atmosphere are, what are the atmospheric weather processes, like clouds? Are there clouds? What is the wind like? How does it blow? What are the molecular compositions? What molecules are present in the atmosphere? If you're looking about terrestrial planets, is there oceans? Is there water? What's the water-atmosphere interaction like? How can that affect the atmosphere? How does the interior influence the atmosphere? And then, of course, everyone's excited about finding these guys producing methane and H2S and what other biogenic gases. And so what I like to emphasize is that the bottom of my screen is cut off, but that's okay. There's nothing important down there. That really the atmosphere is the only observable portion of bodies outside of our solar system. Therefore, any of the information that we get about the processes happening on these planets are going to have to be observed within the context of an atmosphere. So if you want to study surfaces on extrasolar planets, you're going to have to understand the atmosphere. So this is where the light comes from. And the most information content packed way of figuring out what atmospheres are telling us and what the planet is telling us overall is by observing their spectra, right? That's where you get all of the information. And so most of what I'm going to talk about is how we can use spectra to infer basic properties about the atmospheres. And so I stole this from a former postdoc in this department, Shi Zhang, we lovingly called Arthur at Caltech. These are kind of the big pieces that we want to try and understand. You have chemistry. Chemistry is coupled with dynamics. Dynamics is coupled with radiation through these various processes. So understanding all of these pieces of a planetary atmosphere and the links between them is what allows us to come to a more complete understanding. And understanding each of these pieces is non-trivial, especially with the data that we have now. So that was sort of my introduction. So I want to kind of go through two parts. I want to first talk about brown dwarfs and what we can learn about the atmospheres of brown dwarfs from near-infrared spectra. And then based on having given this talk before, There's a 90% chance I will not get to part 2, but that's okay because exoplanets are not that exciting, in my opinion. No, I'm sorry, that's a joke. I love exoplanets. But there's more data for brown dwarfs. So I want to talk about brown dwarfs first because I think they're more exciting. So I like brown dwarfs. Of course, these days you can't just study brown dwarfs. You have to say that they provide context for planets in order to get funding. So that's why we're going to talk about brown dwarfs. And so if you look at this sort of kind of cartoon of sort of the sequence of brown dwarfs, you have something like the sun, then you end up having these M-dwarfs, which are still considered stars, and then some magic happens where you transition from not being a star to being a brown dwarf. You're no longer fusing hydrogen, helium, and then you continue to cool off towards these cooler objects with different spectral indicators dividing these different objects. And then you have these directly imaged planets that sometimes are not sure if they want to be a planet or if they want to be a brown dwarf in between, and then all the way down to our own solar system planets. And so brown dwarfs and planets, they span a continuum of temperatures and masses right here. And so just to kind of recap, you can break brown dwarfs up into these L, T, and then Y spectral classes based off kind of their temperature. And then these are cooling track curves for different masses. So higher mass objects that are older can have similar effective temperatures as lower mass objects that are younger. So there's a little bit of a degeneracy there. This is sort of like a summary of all the brown dwarfs we have right now in a color magnitude diagram. So these are redder objects over here, bluer objects here, dimmer, brighter. So then you have the M's, the L's, and then the LT transition, and then the T's down here. So the idea is that these objects are becoming redder as various clouds are starting to pop into the photospheres of these objects. That's changing the colors. That tends to redden objects, and then some magic happens, and these clouds start to disappear. And then the objects start to look bluer in the near-infrared spectra, and then the clouds eventually start to clear even more, and then they just become fainter and fainter as they continue to cool off. So that's kind of the color magnitude diagram. That is kind of the family portrait of all the brown dwarfs. And just to kind of illustrate the richness of what a spectral data set for brown dwarfs look like, here's just kind of a handful of objects where you can kind of see these transitions going from M's to L's to T's, and you see different spectral features at different wavelengths are beginning to sculpt what these look like. And so these are very rich in information over a wide range of temperatures. So we want to leverage this quality of data. You'll maybe see what some exoplanet data looks like if I get to that. We want to leverage this quality of data to try and understand things like the chemistry and physical processes happening in brown dwarf atmospheres. So what are some of the interesting questions that I'm after when it comes to talking about brown dwarfs? So what are their atmospheric molecular abundances? It's a basic question. What are they made out of? I mean, yeah, hydrogen and helium, but what are the relative ratios of methane, water, CO, TiO, things like that, going beyond just metallicity? Do these molecular abundances vary with altitude? What can this tell us about non-equilibrium chemistry processes? All right. If we have binary systems, how do those elemental abundances of the two objects compare to each other? What can that tell us about how they formed? What are the thermal structures? Can we back out what the temperature is with altitude in these guys? Does it look like objects in the solar system? Do they conform to what we would expect from physics, from radiative equilibrium? Are there non-standard thermal processes like non-LTE heating or other things, or gravity wave breaking that could affect their thermal profiles? What are the observable properties of clouds? Are they patchy? Can we actually learn something about clouds? Clouds are hard. What are the sources of variability? Can variability be explained by clouds or some sort of thermal perturbations? What trends can we identify within the brown dwarf population, and what can that tell us about the atmospheric physics? So if we're able to measure the abundances with temperature, the molecular abundances, what can that tell us about the chemistry that's happening, for instance? And then brown dwarfs with planets, as I mentioned before. Brown dwarfs kind of lay the groundwork because they have way, way better data. And so if we can start to identify the trends and the underlying physical processes governing the workings of their atmosphere, we can translate that in an ambiguous way to planets. So these are the kind of ideas or concepts I want to talk about today, highlighted in red. So the primary tool that I've been using and have been focusing on for the past couple of years to back out brown dwarfs, I'll talk about that in a second, but it's retrieval, this retrieval method. But the traditional way of interpreting brown dwarf spectra comes from this so-called forward modeling or grid modeling approach, where you have a handful of parameters, usually log G and effective temperature, some other stuff. Maybe you have some cloud tuning parameters to model cloud physics in the atmosphere. You count for the distance and the size of the planet and some fudgy factors for underestimated error bars and whatnot. Some, not everyone does this, but and then you assume some physics. You might assume the radiative equilibrium, so you solve for the radiative energy balance in the atmosphere. You assume chemical equilibrium. Sometimes you can assume just equilibrium chemistry. So there's physics that governs given basically a mass of an object and how hot it is. There's some physics that will govern what the atmospheric state will be. And so you can compare that output emergent spectrum from your self-consistent model to the data, and you can kind of get a handle on what these parameters might be. And so just to give you an example of some of these grid model fits here, this is an example of a bunch of different grid models that all make subtly different assumptions. They're all self-consistent in that they're including all of this physics that's self-consistently computing the energy in the atmosphere and the chemistry. But when you compare models that make different assumptions to the same data set, they all derive fundamentally different parameters for the temperature of that object and for the gravity of that object. And so it's often unclear what's causing these differences in these models. Some fit better, some fit worse. So again, most brown dwarfs have been interpreted kind of within this two-dimensional parameter space of log G and effective temperature. Occasionally, there's some additional parameters, but these are kind of all the things we really want to know. We want to know, what are the metallicity, what are properties of clouds, dynamics, things like disequilibrium chemistry. Can we back out the carbon to oxygen ratio in these guys? To the best of my knowledge, there haven't been very many C to O ratio determinations of brown dwarfs. It would be interesting to see how the C to O ratios in brown dwarfs and the brown dwarf population compare to the local stellar population. That's really hard to do using traditional stellar abundance methods. So these are all the things that we hope to learn about these objects, but it's really hard to generate grids of models as a function of all of these different dimensions. There's even more dimensions on here than I could draw. So just kind of take home point from this slide is that these grid models often fail to adequately explain the data. While they have all the physics, clearly they're missing something. Otherwise, they would match the data perfectly. They would match the spectra perfectly. And it's usually because differing model assumptions are at play, and it's often unclear what these different assumptions may be. So the approach that I focus on is this inverse approach or retrieval approach that basically trades off these assumptions of the physical processes happening in the atmosphere for more free parameters, right? If you don't like the way something's fitting, just add more parameters. That's kind of the game we play. But there's some science to be gained in there. So instead of self-consistently calculating what these atmospheres are like, we try and figure out what the data can tell us about the temperature profile in the atmosphere, what the data can tell us about the abundances or gravity, just from the data alone and using the principles of radiative energy transport or just radiative transfer. How do these things affect the emergent flux? And so the idea is that your model effectively calculates these as sort of free parameters. You can then compute your spectrum, and then you can put all this inside a Bayesian framework, which means you couple it with a Markov chain Monte Carlo to estimate what these parameters might be. So can we find the optimal set of abundances or temperature profiles or cloud properties that can explain a given data set? All right. So just to give you a sense for how different molecules influence a spectrum. So most of what I'm going to talk about for the brown dwarfs focuses on the near infrared, so from about 1 to 2.5 microns right here. So for future reference, this is about what the nearest instrument on JWST is going to cover for a lot of transiting planets and brown dwarfs. So this is all, it's going to all be ground-based data for now. But you have water that sculpts out these giant features between these Y, J, H, and K bands right here. You have methane that absorbs strongly on the edge of this H band here, just past 1.6 microns. Ammonia kind of is sculpting out over different areas right here, strongly on this side of this H band. A little bit of H2S absorption. These are all objects that are about 700 or 800 Kelvin. You have the alkali metals that are strongly influencing near 1 micron and near the peak of this J band right here. Gravity kind of affects all wavelengths. And then we're even sensitive to what the temperature is at different altitudes. So if you perturb the temperature at 50 bars, you see an effect on your spectrum where at these wavelengths, whereas if you perturb the temperature at 8 bars, so at higher altitudes in the atmosphere, that only affects these wavelengths. So that's telling you that at these different wavelengths, we're seeing different levels in the atmosphere. So this spectra right here are kind of, directly translates into different altitudes in the atmosphere that we are probing. So that's going to allow us to back out thermal structure information. We can effectively back out the black body at each level in a way. So here's an example of just kind of a retrieval in action. So what I'm showing here is pressure, so higher altitudes up here, deeper, lower altitudes down here. And here's the spectrum right here. So what I want to show is how one of these retrieval methods will converge to a good fit and how the temperature profile has to adjust itself to match this data. Mind you, I'm not showing this, but all the abundances are adjusting themselves along the way as well. So you start out with an initial isothermal atmosphere and you say, okay, adjust the temperature profile to match this spectrum, go. It's hypnotic. And so what you find is that this sort of spaghetti ball of models all have slightly different temperature profiles. And even though there's very little model divergence in the spectrum, there's still quite a bit of divergence in, say, the temperatures. And that all is because there's degeneracies in the atmosphere. So you can trade off temperatures at one level versus another and still obtain the same flux as a function of wavelength. So there's some intrinsic degeneracy that prevents you from obtaining perfect precision. And so this temperature profile, I'll show you in the next couple slides, is actually relaxing to what you would expect from a self-consistent radiative equilibrium model. So what we're retrieving is what we would actually expect, which is kind of nice. And so when you do all that, you can get sort of the degree of uncertainty on things like the water, methane, CO, CO2, ammonia, and these other gas abundances. And so the take-home point here is, at least for these cooler objects, this object right here is about, again, 700 or 800 K. We can get good constraints on the water abundance. We can get good constraints on the methane abundance. We can get good constraints on the ammonia abundance and good constraints on the sodium and potassium abundances. So this is great. So now we have these different species. Now we can start to do chemistry because we have constraints on the molecular abundances. All right. I'll just put this up, but you're like, yeah, retrievals are hokey pokey, or like you said, they're tricks, not treats. You have like a billion parameters, but if you compare, if you do some sort of like Bayesian model selection using, penalizing the number of parameters you have relative to how well retrievals fit compared to some of these self-consistent models, you're justified in using this simpler model with more free parameters. So we can justify using these retrieval models without considering them to be overly complex. So one thing you want to do when you're applying a new tool to some data is you want to validate that tool. So one way of validating these tools, I mean, we've never sent a spaceship to a brown dwarf that I know of and scooped up the gas to figure out what they're made out of. So the closest thing we have to that are these benchmark systems. So benchmark systems are objects, sort of binary systems where you have a star, like a G star or K star, with a brown dwarf companion, and we assume that these guys probably formed at the same molecular cloud, therefore they should both have the same elemental abundances. So the benchmark systems are nice because, well, we don't really know the ages that well, but we know the metallicities of the stars. And so the idea is that if we know the metallicity of the star, we know the metallicity, or the C to O ratio of the star, do the C to O ratios and metallicities of the brown dwarfs that are orbiting them, are they the same? And the answer should be yes, they should be the same under this assumption. And so when you do that, these are these two benchmark objects. So these are two brown dwarfs around 720 Kelvin that both orbit a different companion star. You can back out what the thermal structure is, temperature versus pressure, and the uncertainties on those. You can compare that to what you would expect from radiative equilibrium. This gray box right here is kind of representative of the region where we're more densely probing the atmosphere. So you can think of this as the photosphere, whatever that means for something with large molecular features. So we're really actually getting constraints over this region of the atmosphere. There's some contribution up here, which is what's causing the turnover. And then from this, we can, again, back out the abundances. We can figure out what the influence of including clouds might be. It turns out that these cooler objects tend to be predominantly cloud-free. You don't need clouds to explain their spectra, which is great because clouds are awful. They always kind of obscure what you're seeing, and they're hard to model. Not picking on anyone, but with these T-dwarfs, we just back out that the optical depths of these clouds, if there are clouds, all have to be less than about unity. So that's good. Next thing we do is like, oh, well, I've heard of these retrievals before maybe, and you guys get answers that are crazy with unphysical chemistry. So it turns out with these brown dwarfs that we actually get physically plausible combinations of molecular abundances, e.g. the whole atmosphere isn't made out of methane or H2O or something ridiculous like that. We're getting compositions that are relatively consistent with thermochemical equilibrium proportions. And so if you tune the carbon to oxygen ratio and the metallicity, you can make predictions for what the chemistry is going to be. So the spaghetti on here are the predictions for these different abundances along the temperature structure in the atmosphere, what the molecules, how the molecules would partition. And so you can compare that to our constraints, which are the gray bars, and it's reasonably good. So we get the same correct ordering of water versus methane versus ammonia versus the alkali metals. So that's good. So the retrievals apply to these brown dwarfs, give physically sensible answers. So that's great. And then now we want to back out. How do the elemental abundances in the brown dwarf compare to the elemental abundances from the star? And for these two benchmark objects, this one does pretty good. This one's not quite as good, but it's not that far off. So I think we can safely say that we can more or less move forward with this retrieval methodology on explaining these spectra. And sure enough, you can back out, given the effective temperature and the gravity that we back out from these objects, we can compare that to what we think the age of the stars are. And these particular stars are field stars, so large uncertainties on their ages. We find that the ages we would get with these evolution models applied to a brown dwarf compared to a star are reasonably consistent. So that's good. So not a terrible job. So now we want to move ahead and we want to start looking at these late T-dwarfs. So what can we do in terms of the molecular abundances for an ensemble of these late T-dwarfs here? And again, we're focusing on these late T-dwarfs because they're predominantly cloud-free, so we can kind of eliminate an important degeneracy that kind of inhibits our ability to back out some of the more useful information. So these objects are all between 600 and 800 Kelvin. And just to point out that these are similar effective temperatures to the peak of what the Kepler spacecraft has found for the equilibrium temperatures of transiting planets. So the chemistry that we derive here is directly applicable to most of the transiting planets that we're finding, with the exception of the fact that brown dwarfs have gravities that are 1 or 2 orders of magnitude larger than transiting planets. Another thing that's great about these guys is that they're dominated by water and methane. So if you're measuring an oxygen-bearing species and you're measuring a carbon-bearing species and all of the other carbon and oxygen-bearing species are in relatively low abundance, it's easy to get the C/O ratio. So that's great. So we can actually measure the C/O ratios of these cool brown dwarfs just given the water and the methane abundances. And then these near-infrared spectra provide good leverage on the thermal structure in the atmosphere, so we can get a good handle on the energy balance going on. So this is kind of a family portrait of the 11 objects that I looked at here. Fits are super good. We went over that. We're not overfitting, so that's great. Memorize this. There's a quiz at the end with a scratch card. So I want to, no, I'm just kidding. So what this is just kind of summarizing all of the uncertainty distributions for each of these parameters. So the kind of take-home message here, don't stare at this too long, you'll go cross-eyed, is that there's bounding constraints for all of these objects on water, methane, ammonia, and then the alkalis, which is what you would expect at these temperatures. These are the most abundant species. We'll talk about this in a minute. There's varying degrees of constraints on log G. It's kind of all over the place. Some objects you can constrain it, some objects you can't. It's a function of the signal to noise on the data. And for some objects, we retrieve radii that are larger than what you expect. So for most brown dwarfs, you expect the radii to be between about 0.85 and maybe 1 and some change thereabouts. So for some of these objects, we're getting radii that are extra large. It turns out that those objects are actually binary systems, and you're seeing twice the amount of flux, basically. Twice the amount of flux. So you're going to back out a larger radius if the spectrum that you're looking at is not resolved. So some of these guys are actually blended objects right here. And in all of these objects, we find upper limits on the cloud optical depths, which is interesting, meaning that they're predominantly, they don't have clouds that are thick. All the thermal profiles look roughly the same, and they're all consistent with what you would expect from radiative convective equilibrium, kind of over the region of the atmospheres that we're more sensitive to. So that's great. Deviations above and below this shouldn't be interpreted too heavily. Just because we're not probing this deep, you're usually limited by how far you can deep based off the strength of the collision-induced hydrogen opacities in the atmosphere. So that makes it a challenge there. So this is kind of the exciting part is identifying these trends in the abundances. So what do we have here? So what am I plotting? I'm plotting. So we had the water abundances, the methane abundances, the ammonia abundance, and these alkali metal, sodium and potassium abundances as a function of the temperature that we get for these guys. I should specify the effective temperature is obtained by integrating over the ensemble of spectral fits and computing the sort of bolometric flux from that and equating that to the Stefan-Boltzmann law. So we don't really see any trends in the water, methane, or the ammonia abundances. You can't really strongly reject a flat line in all these cases. But one thing that is emerging that is interesting is this trend in the alkali metals versus effective temperature. So what we're seeing is the alkali metal opacity is decreasing by nearly an order of magnitude over 600 to sort of 800, 850 Kelvin range. We'll talk about what that means in a second. So that's kind of the key important trend here. I specify that with the water and the methane abundances, you don't really expect a strong trend over these temperatures. They're already really abundant, and their abundances don't change too much with temperature under the assumption of solar composition. So another thing you can do is you can back out. If you plot equilibrium condensation curves, so where cloud should form, so where the temperature intersects these dashed lines, cloud should form. Even though I said that we don't have strong evidence for clouds, doesn't mean that a cloud isn't forming. It's just optically thin. So these guys right here are where clouds form. So this is where you would form an N-tight cloud. This is where you would form a salt sulfide cloud, Na2S, and this is where you would form a potassium chloride cloud. And so if you plot up the condensation temperature, or sorry, where these temperature profile, where the retrieved temperature intersects these equilibrium condensate curves where the cloud base would form, think of this as the cloud base as a function of pressure, as a function of temperature right here. So no surprise, as you move towards cooler temperatures, these intersection points are going to happen deeper in the atmosphere. So it also turns out, because there's a correlation of the alkali abundances with temperature, and there's a correlation of the condensation cloud base pressure with effective temperature, there's going to be a trend with the alkali abundances with the cloud base pressure. So the take-home message here is that as the cloud moves deeper in the atmosphere, as you are cooler and cooler and cooler, the amount of sodium and potassium going into the cloud is larger, so the overall column of gas phase sodium and potassium is being decreased, and so we're retrieving an overall lower abundance. So the sodium and potassium are actually tracking, we think, are tracking the sequestration of those species into these two different cloud types. But we're also putting limits on how optically thick those clouds can be. So that's basically just what I said here. As you move towards cooler temperatures, those pressures move deeper. And so what's basically happening as you're moving towards these hotter temperatures, if you plot up the mixing ratio of these species that we're retrieving as a function of equilibrium temperature, these are predicted equilibrium abundances. As you move towards, as you slide the box to the left towards your left, as you slide the box that way, the overall column abundance is lower. So we're probing what's called this rain-out chemistry, where these elements are being locked in these clouds and they're no longer able to participate in the chemistry in the atmosphere. So they're kind of raining out into droplets. That's what we're tracking. So that's kind of cool. There we go. So as I promised earlier, one thing we want to do is we want to back out the carbon-oxygen ratios and metallicities for these guys and compare them to sort of the field stars. So there's this great catalog put together by Natalie Hinkle. She went through and she organized sort of the array of literature values for stellar abundances, which apparently, I guess everyone disagrees on stellar abundances these days. So this kind of represents like an overall kind of average uncertainty on these stellar abundances compared to our objects. One thing I didn't mention is that when you're backing out the carbon-to-oxygen ratio in these guys, or in any object for that matter, anything you're seeing in the atmosphere, you're probing chemistry that could have been affected by chemical processes happening deeper in the atmosphere. And so the actual oxygen inventory that we're probing in the water abundance is actually reduced slightly by about 30%, because a good chunk of that oxygen, about 30% of the oxygen, is going into silicate clouds, enstatite, MgSiO3 and Mg2SiO4. So those guys suck up some oxygen deep in the atmospheres where we're not probing in these guys. And so that actually causes the water abundance we see to be slightly depleted. So that would cause the relative methane to water ratio to be higher than what you would expect. So if you correct for that, if you correct for the fact that you're missing oxygen, this whole set of points moves a little down and to the right. And so kind of in general right here, here's the solar composition is this vertical line right here. I think this object and this object were the two benchmark objects we talked about. We find that the CETO ratios and metallicities with their relatively large uncertainties are sort of consistent more with the tail end here. So it would be nice to populate this figure with more measurements of these objects to see how consistent the brown dwarf CETO ratio distribution is to the stellar population. All right, so moving ahead, one of the questions we might want to ask is, here's another color magnitude diagram. So the sort of flux around 1 micron minus a flux around 1.2-ish microns. You see this drop off in color, and so this has been hypothesized to be due as you go towards cooler temperatures right here. So decreasing spectral type towards these Ys is cooler temperatures. This has been hypothesized to be because of the sequestration of the sodium and potassium being locked up into these cloud species. So one of the characteristics of the Y-dwarfs are these colors right here, where there's basically no more alkali metal opacity in the photosphere. You no longer see it from these near-infrared spectra. So I have a student, JWST, who's working on modeling. He's applying these retrieval methods to a handful of HST wide field camera 3 spectra of Y-dwarfs. They're really hard to do from the ground because they're faint, so you need really stable photometry. He's looking about a sample of 20 objects or so to figure out if how this trend continues. I know he has some more updated stuff I haven't had a chance to put up here. So he's been working hard on this. So that's kind of exciting. Moving ahead, I think working kind of, my plan is to kind of work up and down this color magnitude diagram, because the longer the baseline you have in, say, effective temperature, or the more diversity you have in gravity, the more you can pull out in terms of these trends and maybe say something about the chemistry happening. So here's some nice work from Ben Birmingham trying to look at what we can back out interesting information about the clouds happening in these L-dwarf objects. And so the idea is that he's actually finding for some of these L-dwarf objects that the retrieved temperature profiles are somewhat steeper or somewhat shallower than what you would expect from self-consistent radiative equilibrium models. So maybe this has something to do with some sort of non-standard chemical processes that sort of shift or change the slope of the adiabat in these atmospheres. But I just want to point out that these L-dwarfs are really challenging because you don't often know the cloud properties or ever know the cloud properties, and that you're really degenerate in that case. Just kind of take home message from there. So here's kind of my quick roadmap summary of the brown dwarfs. I think I'm actually going to get to the exoplanets. Oh, shucks. So there's many useful pieces of information in a spectrum that have been largely overlooked. So relaxing these model assumptions can help. We would have never really pulled out that alkali metal abundance trend if we just, tried to slap self-consistent models on top of these things. We've validated this approach, this retrieval approach, on these benchmark systems, and we've learned about these different trends. We can back out things like the carbon to oxygen ratios, something that's not often done for these brown dwarfs. And just quickly pointed out that maybe we can say something of whether or not an object is a binary because we retrieve an unphysically large radius. So now I want to move in and there's some background in kind of the physics we can learn or the chemistry we can do with a small sample of objects with good data. So that's kind of a precursor for what we might be able to do for transiting planets with James Webb. So let's just get right into that. So here's kind of a summary of everything we kind of want to know about planets. This is a nice review paper from Niku Madhusudan, where you have observations of planet mass, radius, we have atmospheric spectra, and then we might know something about the star. So the idea is that you want to synthesize all of these pieces of information to see if you can put together a whole picture of what's going on. So chemical abundances in the atmospheres of planets can maybe combined with the knowledge of the stellar abundances can tell us something about how these planets formed. We'll talk about that more in detail. And then, of course, if we're just interested in the atmospheric processes, these are types of things we might want to know. Whether or not there's heating in the upper atmospheres. Do these guys have stratospheres? How does the wind blow? What are the properties of clouds and hazes? And what's going on with the chemistry? So this is kind of all the things you want to know. This is what I'm going to focus mostly on in here. So most of you guys have probably seen this, so I'll go through this quickly. So there's kind of two ways of, there's more common ways of observing planets. Is either you could directly image them. Turns out there's like, how many are there, Travis? Like 10, something like that, on the order of maybe 15, a dozen, yeah. So it turns out this is really hard. This would be great if we had more of these objects. But the more common way for finding planets is through the transit method. When a planet passes in front of the star, we have something like, 3,000 transiting planets. So how does this work? How do we learn about their atmospheres? When the planet passes in front of the star, kind of looks like a five-eyed alien. That's kind of goofy. There's my Halloween right there. So at different wavelengths, different molecules absorb more strongly or weakly. So it changes the opacity in the atmosphere, making the planet effectively more or less opaque as a function of wavelength and sort of the depth of the spectral features that you see in a spectrum. So if you plot up the kind of radius of the planet that you measure with the time series light curve, if you plot up that transit depth as a function of wavelength, you might see a bump in your spectrum. You might go, there's my Nature paper. I found methane or whatever. And the amplitudes of these features for hot Jupiters, the objects we've been studying more heavily as of late, is about 1 part in 10,000. The reason why we study hot Jupiters is because they have large scale heights. The scale height is the poofiness of the atmosphere governed by how hot it is, its gravity, and then the mean molecular weight, and then Boltzmann's constant, which I think we know pretty well at this point, so we don't have to worry about that one too much. So the idea is that the wavelength-dependent opacity that you measure, the sort of transit depth as a function of wavelength, kind of scales as the log of the abundances times the absorption cross-section. So this kind of information allows us to back out the relative ratios of the abundances of the molecules sculpting the atmospheric absorption. So here's kind of a nice example of a handful of transiting planets from one of David Singh's programs, where a lot of the spectra we see are sculpted by water vapor absorption. So you can just think of this as the radius of the planet. Features that are larger radii are due to opacity sources, mainly due to water here that we're finding in a lot of these hot Jupiters. And then a lot of these objects have these strong power loss slopes that may be indicative of hazes or improper corrections due to star spots. I think there's still some debate as to people working through that right there. Okay, so that's transit spectra. What about secondary eclipse spectra? So transmission spectra can tell us about abundances, and it can tell us about the scale height, things that are happening on the terminator of the planet, the morning and the evening of these planets. They're all tidally locked. So you're seeing the same face. It's looking at the star. So then when the planet passes behind the star, we can do secondary eclipse spectroscopy or occultation. So what you're looking at just before the planet passes behind the star, you're seeing both the flux from the planet and the flux from the star. And when you eclipse the planet, a little bit of the flux of that planet goes away. And so that allows you to back out what the flux of the planet must have been. And that flux, that transit or that eclipse depth changes with wavelength. And that's effectively telling you, different temperatures in the atmosphere. So different depths directly map onto sort of different brightness temperatures that you're probing. So you can piece together an emission spectrum. So if you just overplot two black bodies, you would get a curve like this. You might have a dip in here. The fact that you have a dip here means you're sitting on top of a cooler black body. Usually these dips are proportional to the temperature gradient in the atmosphere. So secondary eclipse spectra if you're measuring at 2 different wavelengths, can tell you something about the temperature gradients in the atmosphere. So these secondary eclipse spectra are great for telling us about the vertical temperature profile in the atmospheres of these planets, in addition to the abundances. So that's great. So here's a nice example of one of the best observed transiting planets. I think this is probably out of date now, where some of this data is no longer considered correct, like this data and some of this data up here. But you can see that there's a lot of information, you know, in this spectra. All these features are being carved out by, you know, water and other gases, which is kind of cool. So let's talk about what we want to learn from some of these hot Jupiters. They have the best signals. They have the best signals. Okay. So I'm not going to have time to talk about chemistry and clouds, but I'll talk about the formation and the thermal structure on these guys. So sort of the crash course in planet formation. I think there's some planet formation folks in the room. You guys can throw something at me when I say something stupid, which I will. There's sort of 2 paradigms in how you form a planet. There's the kind of the gravitational instability. You have a ball of gas and dust. You know, it reaches its sort of Jeans criterion where it collapses, and you might just have a big ball. You might not have a very large core, for instance. And then you have this core accretion, which is this kind of bottom-up approach, where you have a ball of gas and dust. Those pieces of dust stick together like dust bunnies. Something magic happens, blah, blah, pebble accretion. And then you can form these giant 10 Earth mass cores. Did I get that right, Andrew? Okay. That's my pebble accretion, you know, it's magic happens. And then, yeah, right. Oh, yeah, that's a good point. That's important. I guess it depends on who you talk to, too. You know, there's different. Maybe there's magnetic fields. I don't know. And so once you grow to a certain mass, the planet core is able to gobble up the surrounding gas. And then you end up with an atmosphere on top of that. So kind of one of the major focuses have been on looking at some of the consequences of this kind of core accretion method. So we think a lot of the transiting planets probably form via this core accretion. They form further out beyond, say, an ice line and migrated inwards. And then gravitational instability, we think this is a possible avenue for how some of these self-luminous young directly imaged planets that form further out may have formed. So one of the consequences of this core accretion method, this is like woefully out of date at this point, but the basic idea is that as you move further out in your disk, as you know, water becomes less volatile and goes into ices, you leave behind carbon-rich gas at the end. And so the running hypothesis is that if you form a planet here, all the ice goes in the core, all the oxygen goes in the core, and then you slap on some carbon-rich atmosphere on top of that, and boom, your disk goes away, your planet moves inward, and you end up with a planet that has a high C to O ratio. That's sort of the cartoon quick picture here. Another consequence of this is that as you're forming your planet, there's all these leftover planetesimals around. These planetesimals can fall in to the atmosphere, polluting it. And so one of the consequences of that pollution is that the lower the mass of a planet you are, so I'm plotting the metal enrichment, things that aren't hydrogen and helium as a function of planet mass. Because the envelopes are thinner as you go towards lower mass planets, they haven't gobbled up as much atmosphere. They're more susceptible to being influenced by infalling leftover stuff. And so one consequence is you might expect a relationship between planet metallicity and the planetary mass. So a more recent study has looked at whether or not we would have carbon to oxygen ratios that could become large. And because of this because of this infalling accretion of planetesimals, these icy rich planetesimals, things that have oxygen, remember you now have an atmosphere that's sort of carbon rich, now you put all that oxygen back in, it turns out that this planetesimal accretion after you form the atmosphere actually dominates what you think the carbon to oxygen ratio is going to be. And so this nice paper by Christoph Mortesini predicts that most of the carbon to oxygen ratios are going to be much, much less than you would expect via the stellar abundances. So now we have 2 competing hypotheses here, sort of a gas-dominated disk. The atmosphere is dominated by the protoplanetary disk gas, or the atmospheric chemistry is dominated, or composition is dominated by the infalling planetesimals. So these are things we can directly test, these 2 basic hypotheses right here. So how do we do that? Well, we try and we try and back out abundances of these guys. So this is not a brown dwarf spectra. This is a transiting planet spectrum. So limited wavelength coverage. We only have one water band, which is kind of sad. It's really sad. But we can still back out a water abundance. We can't really back out any other molecular species all that well. But taking into account the degeneracies with the temperature, and maybe there's some other molecules that absorb here that we can't constrain very well, taking into account clouds, things like that, we can back out what the water abundances are. This is one of the better observed transiting planets, is WASP-43. You can get a constraint on the water abundances that about plus or minus 1 order of magnitude, around 1 times solar composition. I think the star here was about solar composition as well. So that's great. So one trend, something Jonathan Fortney's been working on, and something that's been noticed in the solar system is this mass metallicity trend that I pointed out earlier. One of the consequences of this co-accretion method, maybe, is that you have lower mass planets that Uranus and Neptune tend to be metal enriched. Jupiter and Saturn are metal enriched, but not as metal enriched. So we can start to put some of these exoplanets on here with their ginormous error bars as is, but maybe there's a trend. So one thing we'd like to do is we'd like to measure the abundances of water or other molecules, get more robust metallicity measurements, and see if this trend is borne out or if there's any breaks in this trend and what that could tell us. What about the carbon-oxygen ratios? Retrievals, they really can't tell you a whole lot. So the carbon-oxygen ratios are very unconstrained in a lot of these transiting planets right now. Looking at transmission spectra, so you can maybe only get upper limits on the C to O ratios. So many of these objects, we can rule out that they have high carbon-oxygen ratios, seeming to favor this idea that the planets are more, the atmospheric composition is more enriched by the infalling planetesimals than it is being dominated by the protoplanetary gas that accreted onto it. So as of now, there's really no good strong evidence for high C to O. The problem is we've only been measuring oxygen species, so how the hell do you get a C to O ratio if you are only measuring oxygen? That's why we're only getting upper limits, because if you make the C to O too high in the atmosphere, equilibrium chemistry will dictate that the water abundance actually, water actually goes away, and then you would no longer see water. So the fact that we're seeing this water vapor absorption feature in these spectra, that's this bump right here, means that there's water, and that water abundance is high enough that it can't be in a regime where the C to O ratios would make that water go away. So that's kind of cool. That's why we get these upper limits. Okay, but that's kind of ratty constraints. Where are we going in the future? In the era of James Webb, hopefully it makes it up okay, because we're all banking on getting spectra that look like this, right? You're like, whoa, holy crap, I'd love to see that CO2 feature right there. That would be amazing. So this is one of the objects in this community early release science program proposal that the transit exoplanet community put in together for this. Who cares what planet it is, but we have some HST spectra for it, and if you use a best fit, that explains that. This is sort of what we would simulate, or what we might expect to find using the different instrument modes proposed in this ERS program. So with data like this is starting to look like the brown dwarf data, even more wavelength coverage here. So instead of getting orders of magnitude constraints on the abundances and loosey-goosey constraints on the C to O ratios and things like that, we can start to get factors of a few. We're actually starting to do planetary science now with the factors of few. That's great. We can get constraints on the species that are more prominent in the spectrum, and that in turn allows us to go from metallicities that are orders of magnitude constrained to metallicities that are to within plus or minus 0.1 or 2 dex, which is great. And then things like the carbon-oxygen ratio we can measure really well. This random aside, this planet's really weird. This planet's in a temperature regime, it's around 800 Kelvin. You would expect methane to be thermochemically prominent at those temperatures. And you would expect a methane bump right here for solar composition. So we're actually retrieving a really low C to O ratio. So solar would be where this tick mark is right here. I cheated when I made this. I made it solar because I didn't want it to be not solar. I imposed my preconceived notion on how I thought it should be bad. But the C to O ratio for this guy seems to be low. So that's kind of interesting. So it'll be interesting to see when we start getting actual spectra for these objects, how they compare to our inferences that we're getting with the current data we have today. And just to give you a sense, we'll be able to really nail the metallicities for a lot of these objects. And with error bars like this, just a handful of objects, we might be able to constrain the slope of this line. The slope of this line could tell you, could tell you the efficiency from which planetesimals are bombarding the planet, or it can tell you maybe the dispersion and the scatter of planets about this line, could tell you about the size distribution of the planetesimals that potentially polluted. That's kind of a stretch. It's all going to need some sort of planet formation model interpretation. People argue these days that if you even have a delta function constraint in the C to O ratio, planet formation theorists would not be able to agree upon what it's telling you. You can correct me, Andrew. But I think the C to O ratio is kind of a hard to interpret kind of measurement. But at least in this case, we can at least start to differentiate between these two different hypotheses. Even if these hypotheses are wrong, we can at least say we have the precision to say whether or not one is wrong or one is right. What's going to end up happening is we're going to measure these things and they're going to be all over the place and we won't be able to tell, but that's science for you. So that's great. So we're going to have the precisions to be able to presumably differentiate different theories. So another option, so I should point out that James Webb is, it's limited time, and unfortunately we have to compete with the cosmologists and the star people and all that stuff. I know the exoplanet folks think we're going to get all the time, but we're probably only going to get maybe a fifth of the time on the telescope. So that realistically means that we might only be able to measure 100 transiting planets. More realistically, we might spend all of our time observing TRAPPIST planets. So that means even less time observing large numbers of hot Jupiters and things like that where you can address formation questions. So an alternative solution is to build your own telescope to do that. So this is some work PI'd by Mark Swain at the Jet Propulsion Laboratory to build a small 75 centimeter telescope. It's called FINESSE, the Fast Infrared Spectroscopic Survey Explorer. It's kind of a backronym, I think. And so we've been selected for a phase 2 concept study. So that means that in 2019, if we do our jobs right over the next year, this thing might actually fly. 2-year mission lifetime, and the basic idea is that it's going to observe sort of with this kind of fidelity from about 0.4 to 5 microns, so nice wavelength coverage over this range. We'll be able to say something about possible hazes in these atmospheres. We'll be able to measure the inventory of carbon molecules. I know these error bars are terrible on what we might get out of the metallicity, but the fact that we have a crap ton of objects, we're going to have maybe 500 to 1,000 objects compared to maybe less than 100 objects with James Webb, we can start to do statistical atmospheric science, which hasn't really been done all that well yet. So that's really the power in these large numbers that's going to allow us to start to identify these trends in atmospheric properties with bulk planetary properties. So what about thermal structure? So that was all about composition. We want to say something about the thermal structure in an atmosphere. Thermal structure in an atmosphere is important. It's important for controlling the energy balance. The thermal structure in all the solar system planets that have substantial atmospheres all tend to have these thermal inversions where the temperature decreases and then begins to increase in altitude. What are the mechanisms that cause that? Do these mechanisms persist around other planets? And so the basic idea with an atmosphere is that you're heated below, some internal entropy, gravitational contraction, and then you're top heated from above, and there's a balance between those, and that's going to govern what the thermal structure is. And so one sort of prediction out of some of these radiative equilibrium models is as you move towards higher and higher temperatures, equilibrium chemistry is going to dictate the presence of titanium oxide and vanadium oxide, which is the sunscreen you wear. Tends to be strong UV optical absorbers. So that causes strong heating in the upper atmosphere. So you might expect that if you were to measure the photospheric temperature gradient, if you were to measure how the temperature gradient behaves as a function of equilibrium temperature of the planet, we might see some goofy trend that looks like this. And so some predictions have suggested that as you go towards even cooler temperatures, you can end up getting the magical photochemical production of hydrocarbon hazes. Tommy, we could probably talk about that. You probably have opinions on that. And that these hazes are dark, they're sooty, they can cause strong inversions in the atmosphere. So maybe we might find a trend where at cooler temperatures, the temperature gradients suggest inversions. There have been some hypotheses that suggest that maybe TiO and vanadium oxide, they end up being cold trapped on the night side of the planets or in a deeper atmosphere, so that you don't end up having that gas in the upper atmosphere available to do the absorption, or maybe these guys actually photodissociate. So we don't really know, so we need to identify what this trend looks like. It's kind of a lot going on there. So point is, we can back out what these thermal profiles look like, and there hasn't really been much evidence for inversions until this study. This is a nice study by David Singh's group, Tom Evans, where they measured a spectrum, a near-infrared spectrum, and it was kind of goofy looking, and that when you try and fit for what the temperature structure would be, you would find that this atmosphere is indeed inverted. And so this sort of represents the first bona fide evidence for thermal inversions in a transiting hot Jupiter, with one possible problem. The atmosphere is mostly made out of H2O, and that the abundance of vanadium oxide, which is causing these emission features right here, this is about 5 orders of magnitude greater than you would expect from equilibrium chemistry. So there's some question as to whether or not that might be 100% a realistic composition there, but the fact that you're seeing these features in emission could mean something, or it means that we're missing, we could be missing something. So this could be one of the dangers of using these retrievals, is that you can fall into these pitfalls where you might think you're explaining a phenomenon. I'm not trashing this or anything, but you have to sort of look at kind of everything that the rest of your parameters, and if you're getting things that are unphysical, you should sort of think about what maybe that means. And I know they try and explain why they might be getting these answers here, but it's really hard to get an inversion this strong to show up at these wavelengths. So something interesting is going on here. So I just decided, because it was fun, to just plot up kind of a family portrait of sort of the highest quality spectra we have of the day side emission of these planets over this wavelength range. So again, this is all from Hubble Space Telescope Wide Field Camera 3. So it's the FP over F star, the eclipse depth. You can convert that into a brightness temperature. So we see a range of temperatures spanning from 500 Kelvin. This is useless down here, to some of these really hot guys between 2,500 and 3,000 Kelvin. And maybe we can start to put together this brightness temperature gradient trend. So basically measuring the maximum temperature gradient over this wavelength region as a function of equilibrium temperature. I mean, maybe you can make a trend out of that, but I really can't. So the idea is that we would want to fill this in. So something like FINESSE and James Webb, we're going to be able to get higher precisions on the constraints of the thermal profile. Definitely having longer wavelengths, higher signal to noises will provide more leverage on that. We might be able to fill out a trend like this, and we can ask whether or not inversions are happening, whether or not they're correlated with higher temperatures, or if they're correlated with mass or gravity or incident UV flux or anything else. So having large numbers, with something like FINESSE, with these types of error bars will allow us to sort of identify what these are. I don't even think we have too many good hypotheses to explain the photospheric temperature gradient with equilibrium temperature. So we'll just have to wait and see what the data would tell us. This is sort of my summary slide, but I just want to leave you with important points about exoplanets that I didn't talk about that I think are going to be important. Phase curve, so mapping how the temperature behaves as the planet goes around the star is going to be very important. That's going to allow us to map out the chemistry and temperature structure. It's going to tell us whether or not our assumption of using 1D models on these intrinsically 3D objects is a terrible idea. Turns out it is. So everything I just showed you is wrong. Except for the brown dwarfs. That's right. That's why brown dwarfs are better. Clouds, yay clouds. They're a hindrance and an opportunity, maybe. But there's something to be learned if we can measure the resonance features. So these clouds are like little crystal lattice thingies vibrating. They give off a spectral feature sort of at longer wavelengths. So one hypothesis is that a lot of the clouds in these transiting planets is due to enstatite, MGSIO3. You might be able to see that like we see in the interstellar medium. We may be able to see that at these longer wavelengths covered by the James Webb MIRI instrument. There's some debate as to whether or not that'll actually happen. If the particles are all large, we won't see that. If the particles are small, as indicated by some of the shorter wavelength data where you see these power law slopes, we might actually see that. Disequilibrium chemistry, I think one of the key things that disequilibrium chemistry is going to tell us is what's driving aerosol production in methane-rich planets. Are we getting the conversion between CH4 and CO right? How does that behave with temperature? the influence of stellar uncertainties on interpreting these spectra, as I alluded to before, you really have to understand the star. You have to understand whether the star is spotty. Oftentimes, you don't know the stellar effective temperature perfectly. There's some uncertainty on that, so that's going to propagate into your temperatures that you get for the planets. That's usually not taken into account. Things like reflected light. So there's a lot of, planets are hard. There's a lot of things going on here. That's why I like brown dwarfs. There's a little bit, less crazy stuff going on. They're not irradiated. That makes them nicer. But in any case, I think the future is bright with these upcoming missions like James Webb, large wavelength coverage. We're really going to nail a couple of objects. Survey telescopes like FINESSE, hundreds to thousands of objects are really going to allow us again to put planetary atmospheric science on kind of a statistical footing. I think that's where we're going. So the idea is that what Kepler has done for our understanding of planet populations and planetary occurrence rates, these future telescopes are going to allow us to do that same thing for the chemistry, physics of planetary atmosphere. So I'll stop right there and take any questions. Yeah. So this is sort of quickly alluded to some of that stuff. Yeah. So the idea with these hazes and clouds, large particle clouds, that creates the me scattering bumps kind of go away. So you end up with these gray-looking spectra that are flat. So we've been really looking over narrow wavelength ranges for a lot of these guys. And so one idea is if you go towards longer wavelengths, like with James Webb, if you think that the wavelength starts to become larger than those particle sizes, you can kind of clear out, and we might be able to see some of these spectral features. Also, some of these spectral features at longer wavelengths, the opacity is stronger there, so you can kind of see the atmosphere above the clouds. So like how long the wavelength? I think going out to 5 microns should do it. Yeah.
So the retrievals that you showed are really cool.
You're like the only person who said that.
No, I think they're great. But what I want to try and get a feeling for is sort of how ready are they to begin ingesting larger data sets than just the spectra?
Oh, for the brown dwarfs.
So yeah, the brown dwarfs. So you mentioned that the spectra are great because they're uniform, high quality.
Yeah.
For example, you also mentioned that longer wavelength leverage is really important.
Yeah, and I haven't included any of that. Yeah, so one of the issues, so I have a problem with using different instruments in different epochs because you end up with these funky offsets between the things, and that's just a matter of me being lazy. You can build that in, you can marginalize over that crap. But yeah, I think including that those longer wavelengths are going to provide more leverage on the temperatures at higher altitudes, and you're also for these cooler objects, the longer wavelengths are going to allow us to better constrain the ammonia abundances as well, and help more firmly identify whether or not we have quenching due to vertical mixing and things like that. They can handle a lot. It also gets a lot slower too when you move towards extended wavelength coverage, and when you go to higher resolution as well. So one of the bottlenecks here is the limit to how long it takes to compute a spectrum. So right now it takes about a second to compute a spectrum. When you start going to an R of 1,000 or an R of 10,000, in order to make sure that you're properly resolving your spectral features in your model, you need to up your sampling. And then you can end up with that equivalent orders of magnitude and slow down. So I think throwing more processors at it can help, or slicker ways of doing computing absorption cross-sections, like correlated K and things like that, can help. No, that's a good question. Yeah, so usually what happens is you have you should have well, in these cases you could have equal brightness binaries would give you sort of that doubling of the flux you would see. So in terms of the composition and stuff like that, I should have flagged those. I wouldn't rely on those too much. So one thing to do is if we flag these, you know, we know we're getting a larger flux. What we should do is we should do like a double retrieval where we have a 2-component model where you double the amount of parameters you have, which is great because you can fit even better. You know, you can maybe do something like you can assume that it's got the same shaped temperature profile, just shifted by some amount or something like that. But you should really try and fit those 2 components. And when we did this at first, it's like, oh, whoa, these guys are, this isn't right, they're big. And then when you go back and look at the literature, like, oh, there's sort of like sketchy evidence that these might be binaries. So it's a good way of looking for binaries. Yeah, but it's a good point.
Foward model, and it's really hard to understand what's going on. On the other hand, there are a few retrieval packages. I was wondering whether there are like comparative studies.
Yeah, so yeah, in terms of like how well do we agree with each other. So I'm sort of been involved in a study for the past year, but it's like a low priority for everyone involved in it because it's not exciting. And if we at James Webb resolutions, if we can retrieve on ourselves, and on the order of maybe 30 part per million precision for transiting, I've done this for transiting spectra, we agree pretty well. So in that sense, for the transiting planets, if we use the same inputs, we agree pretty well. I've compared some of the brown dwarf spectra, just general forward models. You know, if you put in this methane abundance, this CO abundance for some of the brown dwarf spectra, we agree with other groups. But and I think there's been a couple of papers now where I think that Birmingham paper, they also applied their retrieval method, which is a slightly different method, on those 2 benchmark objects, and they got a similar answer as us. So we're agreeing to the level of the uncertainties. But then some are going to be different. I think the divergence is large when you're looking at low signal to noise data. Then your answers are like 100% dependent upon your assumptions and what you include in your model. So that's why there's a lot of controversy in the transit interpretation.
I was instead going to school you quickly on gravitational instability.
Oh, great. No, that's good.
So that theory is about as dead as any theory can be.
Yeah, I figured.
You can still get funding by beating that dead horse, more power to you. But I think what you're learning about the atmosphere is much more interesting.
Yeah.
The question was actually about you showed a lot of models where deep in the atmosphere, which you're not seeing directly, you're getting different TP profiles, different entropies. I'm wondering if there are any cases where you know the mass and radius well enough to try to use that as a constraint.
Yeah, I mean, so the idea is that we could, I mean, you could just pick a point in the atmosphere and you could say, all right, here I'm steeper than the adiabatic lapse rate. I know what the adiabat is supposed to look like for hydrogen and helium, and you could extend that down. But right, yeah, could you have the mass and the radius? You could sort of predict what the effective temperature would be and how much luminosity should be coming out. So you could, in principle, do that. Yeah. Yeah, you could use evolutionary constraints basically as priors. Yeah. Yeah. Hmm?
In terms of FINESSE, the wavelength coverage is rather limited because to interpret that water span absorption, you have to know whether the planets have haze or not in the case of transit. And so you need optical data to be able to interpret the results you will get from FINESSE.
Optical. This is 1 micron. So we're getting less than 1 micron.
So you get
So 0.6 down to about 0.4.
oh, okay.
Yeah.
So 0.4 to
0.4 to 5 microns.
oh, okay.
Yeah. No, we definitely wanted this because we wanted exactly what you said, because you need this to provide context for this.